Hello, welcome to Computer Education for All. Today's topic:
Computer Systems. Unit 1. Introduction. Computer System. A computer system is a fundamental and important part of modern life. It has revolutionized the way we work, communicate, learn, and entertain ourselves. A computer system is not just a single device but a sophisticated combination of hardware and software components that work together to process information, solve problems, and execute a multitude of tasks. Understanding computer systems is very important in today's digital age, whether someone is a casual user or a professional in the field of computing. It empowers the users to utilize the capacities of computers for diverse purposes, from business and scientific research to creative activities and entertainment. A brief history of computer systems and generation. Computers. A computer is a programmable electronic device that performs arithmetic and logical operations automatically using a set of instructions provided by the user. When we study the aspects of computing and computers, it is important to know about the history of computers. Early computing devices. Humans used sticks, leaves, stones, and bones as counting tools before computers were invented. More computing devices were produced as technology advanced and the human intelligence improved over time. A few early-age computing devices are discussed as follows. Abacus. Abacus was one earliest counting devices, consisting of beads or stones on rods or wires. It has been used for centuries in various cultures for arithmetic calculations by sliding beads to represent different numerical values. Abacus is shown in Fig. 1.1. Napier's bone. John Napier developed Napier's bones, a manually operated calculating device. It used 9 separate strips bones marked with numerals to multiply and divide. It was also the first machine to calculate using the decimal point system. Napier's bone is shown in Fig. 1.2. PASCALINE. PASCALINE was invented in 1642 by Blaise Pascal, a French mathematician. It was thought to be the first mechanical and automated calculator. It consisted of a wooden box with gears and wheels in it. PASCALINE is shown in Fig. 1.3. Stepped reckoner or LEIBNIZ wheel. In 1673, a German mathematician named Wilhelm Leibniz improved on Pascal's invention to create this device. It was a digital mechanical calculator known as the stepped reckoner because it used grooved wheels instead of gears. Leibniz wheel is shown in Fig. 1.4. Difference engine. In the early 1820s, Charles Babbage created the difference engine. It was a mechanical computer that could do basic computations. It was a steam-powered calculating machine used to solve numerical problems. Analytical engine. Charles Babbage created another calculating machine, the Analytical Engine, in 1830. It was a mechanical computer that took input from punch cards. It was capable of solving any mathematical problem and storing data in memory. Analytical engine is shown in Fig. 1.5. Tabulating machine. An American statistician, Herman Hollerith, invented this machine in the year 1890. Tabulating machine was a punch card-based mechanical calculator. It could compute statistics and record data or information. Hollerith began manufacturing these machines in his company, which ultimately became International Business Machines (IBM) in 1924. Tabulating machine is shown in Fig. 1.6. Differential Analyzer. Vannevar Bush introduced the first electrical computer, the Differential Analyzer, in 1930. This machine was made up of vacuum tubes used as switches to electrically impulse to do calculations. It was capable of performing 25 calculations per minute. Differential Analyzer is shown in Fig. 1.7. Mark I. The next successful computing machine invented was a digital computer known as Mark I. It was invented by Howard Aiken in 1944. Mark I could add 3 numbers having 8 digits in 1 second. It could print out its results on punch cards or on an electric typewriter. I was 50 feet long, 8 feet high, and weighed about 5 tons. It used 3,000 electric switches. I is shown in Fig. 1.8. Computer generations. History of computers is a chain that runs from the ancient Abacus and the Analytical Engine of the 19th century through the modern quantum computers of present age. It is generally divided into 5 generations. Each generation of computers is characterized by major technological developments of that time. First generation computers 1940 to 1956. First generation computers emerged in the late 1940s and lasted through the early 1950s, were characterized by the use of vacuum tube technology. Vacuum tubes were used as a main electronic devices in the first generation computers. It consists of a glass tube containing electrodes, cathode, anode, and some additional elements in a partial vacuum. A vacuum tube is shown as Fig. 1-9. Tube. The following are some characteristics of first-generation computers. Vacuum tubes were used in first-generation computers. The processing speed was slow. Memory capacity was limited. These massive, occupying entire rooms. First-generation computers were both costly and unreliable. They consumed significant power and generated substantial heat. Input relied on punch cards. Output was obtained through printouts via electric typewriters. Machine language was the only programming paradigm. Some examples of first-generation mini-mainframe computers are ENIAC, UNIVAC I, IBM 604, MARC I, and EDSAC. Second-generation computers 1956 to 1963. Second-generation computers emerged in the late 1950s and extended through the early 1960s. This period marked a significant advancement in computing technology characterized by the transition from vacuum tubes to transistors. Transistor functions like a vacuum tube. It was faster, more reliable, smaller, and much cheaper than vacuum tube. A transistor is 1.10 transistor. The following are some characteristics of second-generation computers. Second-generation computers replaced vacuum tubes with transistors, leading to enhanced efficiency. The adoption of transistors resulted in a reduction in computer by improvements in speed and memory capacity. Second-generation computers demonstrated increased reliability and cost-effectiveness. Key input and output methods included punch card readers, magnetic tapes, magnetic disks, and printers. Assembly language was employed for programming purposes. This generation introduced high-level programming languages such as Fortran and COBOL. Some examples of second-generation computers comprise UNIVAC I, IBM 7030, General Electric GE 635, and Control Data Corporation's CDC 1604 computers. Third-generation computers 1963, 1971. Third-generation computers emerged in the 1960s and extended into the 1970s. This era marked further advancements in computing technology, characterized by the use of integrated circuits ICs and the development of smaller, faster, and more reliable systems. IC chips are shown in Fig.1-11. Fig. The following are the characteristics of third generation of computers. Third-generation computers used integrated circuit IC chips. The utilization of IC chips led to enhancements in computer speed and memory. These computers demonstrated improvements in energy efficiency, size reduction, cost-effectiveness, and reliability compared to second-generation computers. Interaction with third-generation computers involved the use of a keyboard and monitor. These computers had the capability to concurrently run multiple application programs. Do you know? Intel invented the world's first microprocessor, the Intel 4004, in November 1971. Examples of third-generation computers include IBM System 360 and Control Data Corporation's 3300 and 6600 computers. Present. Fourth-generation computers, starting from late 70s to the present, are characterized by significant advancements in technology, particularly the development of large-scale integration (LSI) and very large-scale integration (VLSI) chips. One of the key innovations of this era was the development of the microprocessor, a single chip capable of handling all processing tasks within a microprocessor is shown in Fig. 1 to 12. The following are the characteristics of fourth generation of computers. The introduction of microprocessors marked a defining feature of fourth generation computers, leading to the emergence of microcomputers. Fourth generation computers are known for exceptional speed, large storage capacity, and the incorporation of advanced input-output devices. Microcomputers in this generation are characterized by their small size, high reliability, low power consumption, and affordability. A wide variety of software became available for use in microcomputers during the fourth generation. Operating systems with graphical user interfaces (GUIs) were developed during this period, enhancing user interaction and experience. Fourth generation computers support multimedia software, enabling the integration of text, image, sound, and video. These computers are compatible with modern programming languages such as Visual Basic, C, Java, and Python, facilitating the development of powerful software applications. Fourth generation computers support a diverse range of portable and wireless input-output (CT) devices. Examples of microprocessors developed during this era include the Intel Pentium series, dual-core, Core 2 Duo, Core i3, i5-17, and AMD Athlon. Notable fourth-generation computer models include the IBM ThinkPad series, HP Pavilion series, Dell Inspiron series, as well as Apple's MacBook Pro and MacBook Air series. Fifth-generation computers. The timeline for the fifth generation is not as precisely defined as the earlier generations, but it is generally associated with ongoing advancements in computing that were expected to emerge in the late 20th century and beyond. The main objective of fifth generation of computers is to develop devices that can understand natural languages and have thinking power. This is a big challenge for computer developers to design such systems and software for them. The following are the characteristics of fifth generation of computers. The primary focus of fifth generation computers is to develop and utilize artificial intelligence technologies. This involves machines called robots with the capability to learn, think, innovate, reason, and solve problems automatically and independently. Fifth-generation computers support advanced parallel processing capabilities, allowing them to execute multiple tasks simultaneously and handle complex computations more efficiently. A key aspect of fifth-generation computing is the ability to understand and respond to human languages. This involves developing systems capable of NLP, natural language processing, and communication. Computers are planned to incorporate advanced expert systems, which are software programs designed to replicate the decision-making abilities of a human experts in specific fields, like medical, mining, and engineering. In this generation of computers, user interfaces have become more intuitive and user-friendly, incorporating features like voice recognition and gesture-based controls. Understanding systems and their types. What is a system? A system refers to a collection of interconnected or interrelated components or elements that work together to achieve a specific purpose or function. Systems can be found in various aspects of life, from natural ecosystems to human-made artificial systems. Any kind of system is a group of resources which work collectively in order to produce desired results from given inputs. It accepts input and produces the output. Understanding and categorizing systems is important for various fields including engineering, biology, sociology, and management, as it allows for better analysis, design, and optimization of these systems to achieve their intended goals. Different types of systems may show distinct properties and behaviors, which necessitate different approaches to study and manage them effectively. Natural and artificial systems. Natural systems. A natural system is an interconnected collection of elements or components that exist in the nature. These systems are typically found in the environment, and are characterized by their ability to self-regulate, adapt, and maintain a certain degree of stability. Natural systems are incredibly diverse and fascinating, each with its unique characteristics and interactions. Some natural systems are shown in Fig. 1.13. Fig. Following are a few examples of natural systems. Ecosystems. Ecosystems are perhaps the most common and diverse natural systems. They encompass various types, including forest ecosystems, such as a tropical rainforest with its myriad of plant and animal species. Aquatic ecosystems like freshwater lakes, rivers, and marine ecosystems such as coral reefs. Grassland ecosystems such as the African savanna, home to grazing animals like zebras and wildebeests. Weather systems. Weather systems involve the interactions of the Earth's atmosphere, including phenomena like rainfall, wind patterns, and temperature changes. Geological systems. These systems encompass geological processes and features like plate tectonics, movement of Earth's lithospheric plates, leading to phenomena like earthquakes and volcanic eruptions. Mountain systems such as the Himalayas, formed by tectonic plate collision. Hydrological systems. These systems involve the movement, distribution, and quality of water on Earth, including rivers, lakes, and the water cycle. Solar system. Our solar system itself is a natural system, with the sun, planets, moons, asteroids, and comets all interacting under the influence of gravity. Biological systems. Biological systems encompass a wide range of living organisms and their interactions. Human body, a complex biological system with organs, tissues, cells, and biochemical processes. Coral reef, an ecosystem built by coral colonies and inhabited by various marine species. Rainforest canopy, the upper layer of a rainforest, home to a unique set of plants and animals. Artificial systems. Artificial systems, also known as man-made or human-made systems, are created and designed by humans to serve specific purposes, solve problems, or achieve particular goals. Unlike natural systems, which occur organically in the natural world, artificial systems are intentionally constructed by humans to address various needs and objectives. These systems can range from simple devices to highly complex structures, and they exist in numerous domains. Artificial systems are essential components of modern society, contributing to our ability to meet a wide range of needs and advance in various fields. They often require careful planning, engineering, and maintenance to function efficiently and effectively. Some artificial systems are shown in Fig. 1.14. Fig. The following are some common examples of artificial systems. Communication systems. Telephone networks created to facilitate voice communication over long distances. Internet and computer networks built to enable data sharing and digital communication globally. Satellite communication systems developed for long-distance, wireless communication. Information systems. Databases used for storing and retrieving data efficiently. Software applications such as word processors, spreadsheets, and video editing software. Transportation systems. Automobiles designed for personal and mass transportation on roads. Aircraft engineered for air travel, including commercial airplanes, helicopters, and drones. Trains and rail systems developed for efficient land transportation on tracks. Subways and mass transit designed to move large numbers of people within urban areas. Energy systems. Power plants designed to generate electricity using various energy sources like coal, natural gas, nuclear, or renewable resources. Renewable energy systems including solar panels, wind turbines, and hydroelectric plants. Electrical grids infrastructure for the distribution of electrical power. Manufacturing systems. Factory automation systems that automate manufacturing processes, such as robotics and conveyor systems. Assembly lines organize systems for mass-producing goods. Healthcare systems. Hospital information systems is designed to billing and other healthcare data. Medical devices including MRI machines, X-ray equipment, and artificial organs.
Core components of a computer system. A computer system comprises several core components that work together to perform various tasks. The essential components of a computer system include input devices, output devices, system units, motherboard, memory, CPU, power supply, etc., and data storage devices. 1. Input devices. Input devices are used to provide data into the computer system. Input devices allow us to communicate with the computer. Some commonly used input devices are a keyboard, mouse, microphone, scanner, barcode reader, digital camera, and touch screens. Keyboard. It is the main input device to communicate with the computer. It allows the computer user to enter letters, numbers, and special symbols into the computer. A keyboard is shown in Fig.1.15. Point to pointer ponder. Why the keys on a keyboard are not arranged in alphabetical order. Mouse. It is a handheld device used to control the movement of the cursor or pointer on the screen. It has 2 or 3 buttons at the front that allow the computer user to make selections in the menu, draw graphics or open files, folders, and programs. A typical mouse is shown in Fig.1.16. Microphone. It is a device that allows computer users to input audio into the computer. It changes audio signals into electrical signals which are translated into digital form by the sound card for processing in the computer. A microphone is shown in Fig. 1.17. Scanner. It is a device that captures images from photographs, magazines, books, etc., and stores them in computer in digital form. These images can be edited, displayed on the screen, or inserted in documents. A scanner is shown in Fig.1.18. Barcode reader. It is a device that reads the barcode printed on products that represent product code, description, and price. This information is used by the computer to print bills for the customer. A barcode reader is shown in Fig.1.19. Digital camera. It is an input-output device used to capture pictures and store them in digital form. These pictures can be downloaded to a computer for editing, viewing, or inserting in documents. A digital camera is shown in Fig. 1.20. Touch screen. It is a pressure-sensitive display screen that is used to interact with the computer by touching pictures or words with the finger. Touch screen is more commonly used with mobile phones and tablets. A touch screen is shown in Fig. 1.21. System unit. System unit is the main part of computer. It includes motherboard, power supply, and drives such as DVD and hard disk inside the computer casing. All the input-output devices of a computer are connected to system unit through the ports. Motherboard. Motherboard is the main circuit board inside the system unit. It contains microprocessor, main memory, expansion cards, many IC chips, connectors, and other electronic components. It has many buses, electric pathways printed on it. These are used to transmit information between various components of the computer. All the input-output devices are connected to the motherboard. A motherboard is shown in Fig.1. Microprocessor. A microprocessor is the main chip on the motherboard that controls all the activities of the computer. It is also known as Central Processing Unit (CPU) or simply processor. It contains control unit (CU), arithmetic logic unit (ALU), and registers. A microprocessor and the block diagram of CPU are shown in Fig. 1.23. ALU is the part of the computer that performs all the calculations and comparisons. It consists of an arithmetic unit and a logic unit. The arithmetic unit performs all the arithmetic operations such as addition, subtraction, multiplication, and division. Logic unit performs logical operations which include comparisons of numbers or alphabets. The control unit controls the operations of all the components of the computer. It controls the working of all the input-output devices, storage devices, and ALU. CU loads programs into memory and executes them. It consists of very complicated circuits. Registers are small memory units inside the microprocessor used to temporarily store some information during the execution of a program. Some commonly used registers are the instruction register, accumulator register, data register, and memory address register. Storage devices. Storage devices are used to store programs and data that are not currently used by the computer. They have huge storage capacity. Therefore, they are also known as mass storage devices or secondary memory. A hard disk is the most commonly used storage device that is fixed inside the system unit. Portable storage devices are CDs, DVDs, memory cards, and USB flash drives. Portable storage devices have less storage capacity than hard disks, but they are cheap and easy to carry. Hard disk. Hard disk is a magnetic storage device used to store computer data permanently. It has storage capacity of hundreds of gigabyte GB. It is fixed inside the computer casing. Portable hard disk is also available that is attached to USB. Compact disc CD. CD-DVD is a portable optical storage device with a storage capacity of 700 megabytes MB. A CD is 1.2 mm thick with a diameter of 120 mm. CD drive is used to read data from or write data to a CD. Digital versatile disk. DVD is also a portable optical storage device. It has the same thickness and diameter as a CD but has more storage capacity. Its storage capacity is in the range of 4 to 16 GB. Our DVD writer is installed in the computer to read data from or write data to a DVD. A CD can also be used as a DVD writer. Memory card. A memory card is a small storage device with having storage capacity of a few gigabytes. It is available in different sizes and storage capacities. Memory cards are generally used in laptop computers and portable devices such as mobile phones and digital cameras for storing pictures, audio, and video. A memory card is Fig.1.24 memory card shown in Fig.1.24. USB flash drive. USB flash drive is a small portable drive that is connected to the computer through a USB port. It is also known as USB memory. It is very fast in operation and its storage capacity is up to 128 GB till now. A USB flash drive is shown in Fig.1.25. Or output devices. Output devices are used to display text, graphics, and images on the monitor or to print information on paper. Information displayed on monitor is known as soft copy, and anything printed on paper is known as hard copy or printout. Commonly used output devices are monitor, printer, plotter, and speaker. Monitor. It is an output device that has a screen on which information is displayed. It has two common types, i.e., CRT cathode ray tube monitor and LED light emitting diode monitor. CRT monitor is very similar to old television. It is almost obsolete due to its big size and low display quality. LED monitor is slim, uses less power, and has better display quality than CRT monitor. CRT and LED monitors are shown in Fig. 1-26. Printer. Printer is an output device that prints text and graphics on paper, which is known as hard copy. There are two types of printers, which are impact and non-impact printers. Impact printer. Impact printer uses electromechanical mechanism which causes the character shape to strike against the paper and leave an image of the character on the paper. Dot matrix printer is the most commonly used impact printer. The printing speed varies from 50 to 500 CPS characters per second. Their printing is very cheap but print quality is poor. They produce a lot of noise while printing. These printers are still in use for PR printing invoices, bank statements, utility bills, etc. A dot matrix printer is shown in Fig. 127A. For your information, the first high-speed printer was developed in 1953 by Remington Rand, an early American business machines manufacturer for use on UNIVAC computer. Non-impact printer. Non-impact printer prints without striking the paper. There are two types of non-impact printers, which are inkjet and laser printers. Inkjet printer stores ink in cartridge and sprays on paper through fine nozzles on the print head. Laser printer uses technology similar to photocopying machine. Laser printer is more expensive, faster, and has very high print quality compared to inkjet printer. Inkjet printers are used in all sectors such as homes and simple businesses. Laser printers are perfect for large-scale businesses. Inkjet and laser printers are shown in Fig.1.27.BC. Plotter. Plotter is an output device used for printing engineering drawings, machine parts, building designs, maps, charts, and panoflexes, etc. on large-size paper sheets. Such large-size printing is not possible on printers. It is more expensive than printer. There are two types of plotters, that is, ink plotter and pen plotter. Ink plotter is used for printing images, whereas pen plotter is used for printing engineering drawings, machine parts, building designs, etc. Plotter is a slow output device, but its printing quality is good. A plotter is shown in Fig. 1.28. Speaker. Speaker is a device used to produce audio output. A pair of speakers are attached to the sound card on the motherboard. Speakers are commonly used with multimedia software and for playing music and videos on computer. A pair of speakers are shown in Fig. 1.29. Ports, expansion slots, and expansion cards. Ports. Port is an interface for connecting various devices to the system unit. These are located on the motherboard and are usually seen at the back of the system unit. There are various types of ports for connecting keyboard, mouse, monitor, microphone, speakers, and other input-output devices as shown in Fig. 1.30. In modern computers, USB Universal Serial Bus, HDMI High Definition Multimedia Interface, DVI Digital Visual Interface, audio and LAN Local Area Network ports are used for connecting various devices to the computer. These devices include digital camera, scanner, printer, external hard disk or DVD writer, and USB memory. Expansion slots and expansion cards. Expansion slots are long, narrow sockets on the motherboard used for installing expansion cards. Expansion cards are small circuit boards. These cards add new capabilities to the computers. Commonly used expansion cards are sound card, graphics card, modem card, and network card. In modern computers, these cards are built in on the motherboard. A network card is shown in Fig. 1.31. Von Neumann architecture is an essential concept in computer science that explains how a computer's hardware and software work together to process information. It was first published by John von Neumann in 1945. His computer architecture design consists of a control unit, arithmetic and logic unit, ALU memory unit, registers, and inputs/outputs. Von Neumann architecture is based on the stored program computer concept, where instruction data and program data are stored in the same memory. This design is still used in most computers produced today. Modern von Neumann architecture is shown in Fig. 1.32. Central Processing Unit CPU. The Central Processing Unit CPU is the main electronic circuit responsible for executing the instructions of a computer program. The CPU contains the LU, CU, and a variety of registers. Registers are high-speed storage areas in the CPU. All data must be stored in a register before it can be processed. MA memory address register holds the memory location of data that needs to be accessed. MDR memory data register holds data that is being transferred to or from memory. AC accumulator where intermediate arithmetic and logic results are stored. PC program counter contains the memory address of the next instruction to be executed. SAR current instruction register contains the current instruction during processing. Arithmetic and logic unit ALU. The ALU allows arithmetical add, subtract, etc. and logical and or not etc. operations to be carried out. Control unit CU. The control unit controls the operation of the computer's ALU, memory, and input-output devices, telling them how to respond to the program instructions interpreted from the memory unit. The control unit also provides the timing and control signals required by other computer components. Control unit is shown in Fig. 1.33. Buses. Buses are the pathways or lines by which data is transmitted from one part of a computer to another, connecting all major internal components to the CPU and memory. A standard CPU system bus is comprised of a control bus, data bus, and address bus. Address bus carries the addresses of data, but not the data between the processor. Data bus carries data between the processor, the memory unit, and the input-output devices. Control bus carries control signals or commands from the CPU in order to control and coordinate all the activities within the computer. Memory unit. In von Neumann architecture, the memory unit consists of RAM and cache memory, sometimes referred to as primary or main memory. This memory is fast and also directly accessible by the CPU. RAM is split into partitions. Each partition consists of an address and its contents both in binary form. The address uniquely identifies every location in the memory. Memory unit is shown in Fig.1.34. Input-output 1/0 controller. This component manages the flow of data between the CPU and external devices like hard drives, USB devices, and network interfaces.
Data transmission within a computer system. Data transmission within a computer system involves the movement of data/information between various components such as the CPU memory, storage devices, and input/output devices. This process is vital for the proper functioning of a computer and its ability to execute tasks efficiently. The following points give an overview of how data is transmitted within a computer system. Bus architecture. Computers use a bus architecture to transmit data. A bus is a communication pathway that allows the transfer of data and control signals between various components, such as the CPU memory and peripheral devices. It is just like a highway system for data inside the computer system. There are different types of buses. Data bus carries the actual data being transmitted. Address bus specifies the location in memory or I/O device where data should be read from or written to. Control bus carries control signals that manage the data transfer process, for example, read, write, halt, etc. Data paths. Inside the CPU data paths are dedicated paths known as data circuits that facilitate the movement of data between various functional units. These functional units include the arithmetic logic unit, ALU registers, cache, and other components involved in data processing. The data paths allow the CPU to perform operations on data by providing routes for data to move within the processor. Data paths are more internal and pertain to how data moves within the CPU, while bus architecture addresses the broader communication infrastructure that enables data transfer between the CPU and other parts of the computer system. Details are shown in Fig. 1.36. Registers. Registers are small, high-speed storage units located within the CPU. They hold data that is frequently used by the CPU during processing. Data is quickly transferred between registers and main memory via the buses. Memory hierarchy. Modern computers use a memory hierarchy to improve data transmission. Data is stored in different levels of memory, ranging from high-speed but small cache memory to larger and slower RAM, and even slower secondary storage, hard drives, SS. The CPU fetches data from the higher levels of the hierarchy, first due to their faster access times. Instruction cycle. When a program is executed, it goes through a series of steps called the instruction cycle. This cycle involves fetching the next instruction from memory, decoding it to understand what operation is required, fetching operands from memory or registers, executing the operation, and storing the results back in memory or registers. It is called fetch, decode, execute cycle. Pipeline processing. Many modern PUs use pipelining to increase efficiency. In a pipeline, multiple instructions are in different stages of execution simultaneously. This allows for better utilization of the CPU's resources and faster execution of instructions. Interrupts. NI/O input/output devices, for example, keyboard, mouse, display, network interface, communicate with the CPU using interrupts. An interrupt is a signal that halts the current program's execution to handle an important event. This allows data to be transmitted between the CPU and these devices. Parallelism. Some computer architectures use parallelism to improve data transmission speed. This can involve multiple cores within a CPU or even distributed systems with multiple interconnected computers working together.
Types and hierarchy of computer memory. In computing, memory refers to the physical devices used to store programs, sequence of instructions, or data on a temporary or permanent basis for use in a computer or other digital/computing devices. Memory in a digital computer contains the main part of the operating system and all the application programs and related data that are being used. Fig. 1.37 shows different types of computer memory. Memory terminology. The following are some important memory terms. Bit. The smallest unit of memory in digital computer is a bit, which stands for binary digit 0 or 1. The memory of a computer consists of millions of memory, or electronic cells. Each cell contains one bit of information. The memory cell has two states, on and off. The on state represents a binary 1 and off state binary 0. Byte is the basic unit of computer memory, and it is the minimum piece of data to be processed by a computer. A group of 8 bits is known as 1 byte. 1 byte of memory is required to store one character in the computer. For example, a byte is generally used to express the memory size of a computer. Computer memory is measured in terms of bytes. The higher units are kilobyte, KB, megabyte, MB, gigabyte, GB, and terabyte, TB. In the future, memories will also be available in petabyte, PB, and exabyte. Memory word in computing. The smallest amount or size of data that a computer can process is called a memory word. It is a fixed-size piece of data handled as a unit by the processor. The number of bits in a word is called the word size. Word size in modern computers typically ranges from 16 to 64 bits, depending on the size of the computer. A computer that has a bigger word size can transfer more bits into the microprocessor at a time for processing, and this improves the processing speed of the computer. The relationship between the memory units is shown in Table 1.1. Let's define the relationship between the memory units are equivalent to is shown in Table 1.1. 1 bit, 1 bit. 1 nibble, 4 bits. 1 byte, 8 bits. 1 kilobyte, 1024 bytes. 1 megabyte, 24 kilobytes. 1 gigabyte, 24 megabytes. 1 terabyte, 24 gigabytes. 1 petabyte, 24 terabytes. 1 exabyte, 24 petabytes. 1 zettabyte, 24 exabytes. In the future, memories will also be available in petabyte, PB, and exabyte. EB as indicated in red color in Table 1.1. Memory built-up and retention power. All types of computer memory, as far as their built-up or manufacturing is concerned, are divided into chip memory, magnetic memory, and optical memory. And as far as their retention power is concerned, these memories are divided into volatile memory and non-volatile memory. Chip memory. A chip is a small piece of semiconducting material, usually silicon. A small circuit called IC integrated circuit is embedded on it. A typical chip contains millions of electronic components, transistors. Chip memories are better in speed compared to other memory types due to the absence of mechanical moving parts. Unlike traditional forms of memory, chip memories rely on electric currents for their operation. This reliance on electrical processes contributes to their rapid data access and retrieval capabilities. Examples of chip memory are main memory, RAM, ROM, and cache, flash memory drives, memory cards, registers, and solid-state drives,
SDs, many special-purpose chips, known as application-specific integrated circuits, are also being made today for automobiles, home appliances, telephones, and other devices. Different types of chip memory devices are shown in Fig. 1.38. Magnetic memory. One of the most widely used types of digital data storage is magnetic memory/storage. This refers to any type of data storage using a magnetized medium. Magnetic tapes and disks are examples of magnetic memory devices. A thin layer of magnetic material is coated on the magnetic disk read/write head. Surface of magnetic tape and magnetic disks. Binary information is stored in the form of tiny magnetized and non-magnetized spots on the surface of magnetic tape or disk. A magnetized spot represents a binary 1 and a non-magnetized spot a binary 0. A read-write head moves very close to the magnetic surface. The head is able to detect and modify the magnetization of the material. Magnetic storage is widely used because it is relatively cheap in comparison with other storage technologies. The storage capacity is also very large, making it attractive for storing very large amounts of data. The major limitation of magnetic storage is that accessing the data can be quite slow. Hard disk is the common example of magnetic memory as shown in Fig. 1.39. Do you know? In September 1956, IBM launched the 305 RAM AC, the first UPER computer with a hard disk drive, HDD. The HDD weighed over a ton and stored 5 MB of data. Optical memory. In optical storage technology, a laser beam encodes digital data onto an optical disc in the form of tiny pits and lands arranged in concentric tracks on the disk surface as shown in Fig. 1.40. A low-power laser scanner is used to read data or information from these pits and lands and converts it to digital form. Optical storage provides cheaper and greater memory capacity than magnetic storage. An entire set of encyclopedias, for example, can be stored on a standard 12-centimeter, 4.72-inch optical disc. Optical discs include CDs, DVDs, and Blu-ray discs. Main memory. Main memory stores data and programs that are being executed by the computer. It also stores the results produced by the ALU after processing the data. There are 3 types of main memories on the motherboard, which are ROM, read-only memory, RAM, random access memory, and cache. These are known as main memory or primary memory of computer. ROM, read-only memory. ROM is a single IC chip which is installed on the motherboard as shown in Fig. 1.41. It stores the basic input/output system BIOS of computer that controls input/output devices and the startup or boot process BIOS programs test the computer's components when it is turned on and then load the operating system into the RAM to make the computer ready for operation. BIOS programs are permanently stored in ROM when it is manufactured. It is non-volatile memory, that is, the programs stored in it are not lost when the computer is turned off. There are 3 common types of ROM, which are PROM, programmable ROM, EPROM, erasable programmable ROM, and EEPR, electronically erasable programmable ROM. RAM, random access memory. RAM is high-speed memory installed on the motherboard. It is read and write memory.
Information can be read from or written into it. Programs are loaded into RAM from secondary storage devices such as hard disk or USB flash drive for execution by the microprocessor. It is volatile memory, which means information stored in it is lost when the computer is turned off. RAM modules are installed in the memory slots on the motherboard. RAM modules are shown in Fig. 1.42. Cache memory. Cache is a very small amount of extremely fast memory inside the microprocessor or on the motherboard. It is faster and more expensive than RAM. It stores information that is most frequently used by the computer. The purpose of using cache is to improve the processing speed of computer. There are 3 types of cache memories, which are Level 1, Lone, Level 2, L2, and Level 3, as shown in Fig. 1.43. L1 cache is built inside the microprocessor, whereas L2 and L3 are on the motherboard. L1 cache is faster than L2 and L3 cache. Volatile and non-volatile memory. Memory on the divided into 2 types, volatile and non-volatile memory. Volatile memory. Volatile memory is a temporary memory that requires power, electricity, to maintain the stored information. Volatile memory retains the information as long as power supply is on, but when power supply is off or interrupted, the stored memory is lost. It is also known as temporary memory. Examples of such memory are RAM, random access memory, cache memory, and registers. Non-volatile memory. Non-volatile memory is a permanent memory that can retain the stored information even when powered off. Examples of non-volatile memory include ROM read-only memory, flash memory, magnetic storage devices,
For example,
hard disks and magnetic taps, optical disks, and Blu-ray discs. Non-volatile memory is typically used as secondary storage for long-term or future use. Computer software. Computer software, often referred to simply as software, is a collection of programs, data, and instructions that tell a computer how to perform specific tasks or functions. It is an important component of any computer system, enabling it to process data, run applications, and interact with users. Software is typically categorized into 2 main types: system software and application software. Computer software can be classified into the following types: system software, application software. System software. System software refers to a type of computer program that manages and controls the hardware components of a computer system, as well as provides a platform for running application software. It plays a crucial role in enabling interaction between the user, application software, and the underlying hardware. System software serves as an intermediary between the user and the hardware, making it easier for users to interact with and utilize computer systems effectively. The following are some common types of system software: operating system OS, device drivers, utilities, compiler and assembler, linkers and loaders, firmware, operating system OS. The operating system is a fundamental type of system software that manages hardware resources and provides services for computer programs. It controls tasks such as process scheduling, memory management, file system management, and hardware device communication. Common examples of operating systems include Microsoft Windows, MacOS, Linux, and Android. Some common functions of OS include: the OS facilitates user interaction by providing a user-friendly interface. It manages input/output operations. It looks after the allocation of tasks to the processor. It handles the allocation and deallocation of memory to programs. It helps in organizing files and directories, as well as provides mechanisms for storage and retrieval. It manages peripheral devices, such as printers and storage devices, and provides necessary device drivers. It provides security and access control through user authentications, like user identifications, passwords, and PINs, etc. Device drivers. Device drivers are software components that facilitate communication between the operating system and hardware devices like printers, graphics cards, and network adapters. They ensure that the OS can interact with these devices correctly. Utilities. System utilities are tools that help manage and maintain the computer system. They can perform tasks such as disk cleanup, data backup, system monitoring, and virus scanning. Examples include disk defragmenters, antivirus software, and system diagnostic tools. Compiler and assembler. These tools are essential for converting high-level programming languages like C++, Java, or Python into machine code that the computer's processor can understand. Compilers translate high-level language code, source code, into executable programs, while assemblers do a similar job for assembly language code. Linkers and loaders. Linkers and loaders are programs that help with the execute of programs. Linkers combine multiple object files, compiled code, into a single executable file, while loaders load these files into memory for execution. Firmware. Firmware is a type of software that is permanently stored on hardware devices. It provides low-level control over the device's operation. Examples include the BIOS, Basic Input/Output System, in a computer's motherboard, or the firmware in application software, often referred to as apps or software applications, is a category of computer programs designed to perform specific tasks or functions for computer users. Unlike system software, which manages and controls the hardware and provides a platform for running applications, application software is created to address the various needs and requirements of users. Some examples of application software are productivity software, business software, entertainment software, educational software, productivity software. Productivity software is designed to help users perform tasks efficiently, organize information, and create contents like documents, presentations, spreadsheets, and databases. It includes software that facilitate office work, document management, and collaboration. Examples: Microsoft Office Suite includes applications like Microsoft Word, word processing, Excel, spreadsheets, and PowerPoint presentation. Google Workspace offers tools like Google Docs, Sheets, and Slides for online collaboration and document creation. LibreOffice, a free and open-source office suite with applications similar to Microsoft Office. Business software. Business software are specifically designed to meet the needs of businesses and organizations. These software aim to streamline and enhance various aspects of business operations, ultimately improving efficiency, productivity, and decision-making. Examples: QuickBooks, accounting software for managing financial transactions and generating reports. Salesforce, customer relationship management, CRM software for sales and marketing. Trello, project management tool that helps teams organize projects. Entertainment software. Entertainment software is designed for leisure and enjoyment. It includes a wide range of applications, from video games to multimedia players and streaming services. Examples: Minecraft, a popular game that allows players to build and explore virtual worlds. Spotify, a music application that offers a vast library of songs and playlists. Netflix, an online streaming service for movies, TV shows, and documentaries. Educational software. Educational software is created to support learning and skill development. It includes a variety of applications and tools that support educational activities, ranging from interactive learning games to digital resources for teaching and assessment. Examples: learning management systems, LMS platforms provide a centralized place for educational content, resources, assessments, and communication between educators and students. Some examples are AIOU,
Agahi LMS, Virtual Academy, FBIS, LMS, etc.
Kahoot, an online learning platform that allows educators to create interactive quizzes and games for students. Duolingo, language learning app that gamifies the process of learning new languages. Scratch, a visual programming language for teaching coding concepts to children. Programming languages. A programming language is a structured and systematic method of communicating instructions to a computer. It consists of a set of predefined commands, syntax, and rules that allow programmers to write instructions, enabling the computer to perform specific tasks or solve problems. It serves as a means of communication between a human programmer and a computer, facilitating the development of software and applications. Programming languages can be classified into two categories, that is, low-level languages and high-level languages. Low-level languages. Low-level language is machine-oriented language. To understand low-level language, detailed knowledge of internal working of computer is required. Low-level languages include machine language and assembly language. Machine language, programming language that is directly understood by computer hardware, is known as machine language. Machine language is associated with architecture of computer. Therefore, programs written in machine language for one computer will not work on another because of design differences. It consists of OS and 1S. It is almost impossible for humans to use machine language because it entirely consists of numbers. Therefore, practically no programming is done in machine language. Instead, assembly languages and high-level languages are used. Assembly language consists of symbolic codes or abbreviations known as mnemonics. It was developed to make computer programming easier than machine language. The abbreviations used in assembly language make it easier to learn and write programs compared to machine language. A program written in assembly language must be converted into machine language before it is executed by computer. A program known as assembler is used to translate assembly language into machine language. Some important characteristics of assembly language are: assembly language allows programmers to have access to all the special features of the computer they are using. Certain types of operations, which are not possible in high-level languages, are easily programmed using assembly language. Generally, a program written in assembly language
will require less storage and less running time than one prepared in a high-level language. Assembly languages are still the best choice in some applications, but their use is gradually declining. High-level languages, HLLs. High-level languages are English-oriented languages, and they are commonly used for writing computer programs. These languages use English language words such as print, goto, if, end, etc. Therefore, they are easy to learn and use. Some examples of high-level languages are Visual Basic, C, Java, and Pascal. A program known as compiler/interpreter is required to translate a high-level program into machine language. Coding and debugging of a high-level language program is much easier than a program written in a low-level language. High-level languages can be classified into procedural, structured, and object-oriented programming languages. Procedural and structured languages. Procedural programming is based upon the concept of modular programming. In modular programming, programs are divided into smaller parts known as modules. Modular programs consist of one or more modules. A module is a group of statements that can be executed more than once in a program. Each module in a program performs a specific task. It is easy to design, modify, and debug a program in a procedural language since it provides better programming facilities. Structured languages consist of three fundamental elements, which are sequence, selection, and repetition. Sequence, it means writing program statements in a logical sequence. Each step in the sequence must logically progress to the next without producing any undesirable effects. Selection. It allows the selection of any number of statements based on the result of evaluation of a condition which may be true or false. Examples of statements that implement selection in programming are if, else if, switch, etc. Repetition, loops. It means executing one or statements a number of times until a condition is satisfied. Repetition is implemented in programs using statements such as for and while loops. Some examples of structured and procedural languages are Fortran, Pascal, C, Basic, Algol, PL/1, and Ada Pascal. Object-oriented programming languages. Object-oriented programming, OOP, refers to a programming method that is based on objects such as student, vehicle, building, etc. Object-oriented programming language provides a set of rules for defining and managing objects. An object can be considered a thing that can perform a set of activities. For example, the object vehicle can be defined as an object that has number of wheels, number of doors, color, number of seats, etc. The set of activities that can be performed on this object include steer, accelerate, brake, etc. Complicated large computer programs are difficult to design, develop, maintain, and debug. The concept of object-oriented programming solves this problem. The most widely used object-oriented programming languages are C++, Visual Basic, C, known as C#, and Java, uses of low-level languages. Important uses of low-level programming languages include use explanation, operating system development writing the core software that manages hardware resources, device drivers creating software to enable communication with hardware devices, embedded systems programming microcontrollers and lot devices for specialized functions, firmware development developing software that resides on hardware components, real-time systems ensuring precise timing and responsiveness in industrial control, robotics, and aerospace systems, security tools building intrusion detection, firewalls, and encryption software for robust security, game development optimizing game engines, physics simulations, and graphics rendering for performance. Uses of high-level languages. Important uses of high-level programming languages include use explanation, applications, Apps, development creating desktop, mobile, and web applications. Apps for various platforms. Web development high-level languages are used to build websites, making them interactive and functional. Data analysis and science analyzing large datasets and conducting scientific research. Machine learning and AL developing machine learning models and AL algorithms. Automation and scripting, automating tasks and processes, including system administration and data manipulation. Game development, developing gameplay logic, AL, and user interfaces for games. Database management, creating, querying, and managing databases. Scientific and engineering simulations, simulating complex systems and conducting simulations. Business software, developing enterprise-level software for various industries. Educational tools, creating e-learning platforms and educational software. Data communication. Data communication refers to the process of exchanging data or information through a computer network between two or more devices or systems through a transmission medium such as cables, optical fibers, or wireless mediums. This communication can involve the transfer of various types of data, including text, numbers, images, audio, and video, and it is a fundamental component of modern information technology and telecommunications. A simple communication network having wired and wireless connections is shown in Fig. 1.44. Network communication components. Data communication is the process of transferring information from one point to another in a networking environment. Network communication consists of 5 basic components, as shown as Fig. 1.45. Sender, message, medium, protocol, receiver. Sender, also called transmitter, is a computer/device that sends the message, data, or information from source to destination in a communication network. It may be a computer, workstation, cell phone, or camera. The sender device converts the electrical signal into a form that is suitable for transmission over the communication network. Message. Message is the data or information that is to be transmitted. Message can be in the form of text, audio, video, or any combination of these. Medium. Medium is the path through which message travels from source to destination. A medium can be wired, for example, telephone cable, coaxial cable, and fiber optics. It can also be wireless, for example, Bluetooth, Wi-Fi, microwave, radio wave, and satellite. Receiver. Receiver is the device which receives transmitted message. It can be a computer, workstation, telephone handset, or television set. The data received from the transmission medium may not be in proper form to be accepted to the receiver, and it must be converted to appropriate form before it is received. Protocol. A protocol is a set of rules that governs data communications. It represents an agreement between the communicating devices. Without a protocol, two devices are connected but may not communicating with each other. Modes of network communication. Modes of network communication refer to the methods or the ways information is transmitted from one place to another. The following are different modes of data communication: simplex, half-duplex, and full duplex, synchronous and asynchronous. Simplex mode. In simplex mode, the communication takes place in only one direction. In this mode, communication is unidirectional. The communication can only take place in one direction, and it is not possible for the receiver to send data back. For example, Data is sent to an electronic notice board found in train stations and airports, as shown in Fig 1.46. Radio and television broadcastings are also examples of simplex transmission. Half-duplex mode. In half-duplex mode, the communication takes place in both directions, but not at the same time. The signal can only be sent or received at one time. A common example of this type of communication is the use of walkie-talkies as sender/receiver, shown in Fig 1.47, where each of the persons communicating must indicate when they have finished speaking. Half-duplex transmission is used also in transaction-oriented systems, for example, communication between a computer and a credit card machine. Full duplex mode. In full duplex mode, the communication takes place in both the directions at the same time. In this mode, both sender and receiver can send and receive the data simultaneously. For example, when two computers communicate with each other to send and receive some data, as shown in Fig 1.48, it is the fastest bidirectional mode of communication. The full duplex mode is like a two-way street, with traffic flowing in both directions at the same time. One common example of full duplex communication is the telephone network. When two people are communicating by a telephone line, both can talk and listen at the same time. Asynchronous transmission. In asynchronous transmission, the time interval between two characters is variable and not fixed, as shown in Fig 1.49. The computer devices can exchange information at their own rate, slow or fast. Start and stop bits are used in asynchronous transmission. These bits provide timing, synchronization, for the connection between the sender and the receiver. The start bit tells the receiver that a character is coming, and stop bit indicates that the transmission of character has ended. This type of transmission is ideal for slow-speed communication when gaps may occur during transmission. Example of asynchronous transmission is keyboard data transmission. Synchronous transmission. In synchronous transmission, the time interval between two characters is always the same as shown in Fig 1.50. In this method, two communicating devices are synchronized, and they continue to send characters in order to remain synchronized, even if there is no data to be transmitted. A special idle character is sent when there is no data for transmission. It does not require transmission of start and stop bits. It sends data as one long bit stream or block of data, and each bit is sent one after the other. The receiver counts the bits and reconstructs the sent information in bytes. It is essential that timing is maintained, as there are no start and stop bits and no gaps. Accuracy dependent on the receiver keeping an accurate count of the bits as they come in. Synchronous transmission is faster than asynchronous because fewer bits have to be transmitted, i.e., only data bits and no extra control bits are sent. The best example of synchronous transmission is the data transmission between devices in network communications links. Communication devices. A device that is used in telecommunication systems for transmitting data from one location to another is known as communication device. Commonly used communication devices are hub, switch, router, and gateway. Hub is a connectivity device used in LAN. It connects multiple LAN devices on one network and makes them act together as a single network. A hub is a non-intelligent device and sends output to all the devices on the network. A hub has multiple input/output, I/OA ports, in which an input in one port results in it being an output in all the other ports, except the port where it was input. A hub is shown in Fig 1.51. Switch is a networking device that performs the same job as the hub, but are considered as intelligent than hub. it gathers information about the data packet and forwards it to only the node, e.g., computer it was intended for. A data packet is a basic unit of communication over a computer network. When data is transmitted, it is broken down into packets, which are reassembled to the original form once they reach the destination. A switch is shown in Fig. 1.52. Router. Router is a communication device which is used to connect two or more networks. Today, most of the networks are connected to Internet. When the computer is sending data to another computer on the Internet, router receives the data packets, looks for the remote computer address, and forwards it to a computer that is closer to the remote computer. It forwards the data packets by selecting the best pathway based on network traffic. Many routers take part in transmitting the data packets from one location to another. A wireless router is shown in Fig. 1.53. Gateway. Gateway is a device that is used to connect a network to another network that uses different protocols. If we have to link different kinds of networks, such as a network of IBM mainframe computers and a network of Cs, we might have to use a gateway. Gateways change the format of the data packets, but not the contents of the message, to make it conform to the application program of the remote computer. A gateway is shown in Fig. 1.54. Network architecture. Network architecture is the design of a communication system. It includes hardware devices, such as routers and switches, cabling, network topology, and physical and wireless connections. Computer networks consist of server computers and client computers. Server computer, a computer on the network that shares resources for others to use, is called a server computer or simply server. Shared resources include information, software, printer, plotter, internet connection, hard disk, etc. Client computer, a computer on the network that accesses resources that are shared by other computers, is known as client computer or simply client. The two commonly used network architectures are client/server network, peer-to-peer network, client/server network. A computer network in which each computer on the network acts as either a server or a client is called client/server or dedicated server network. Each server computer on the network is called a dedicated server. Servers are not used as client computers. Fig. 1.55 illustrates how a dedicated server network may be designed. The computer at the top of the figure is the dedicated server, sharing files and applications. The remaining computers in the illustration are clients that access resources shared by the server. Similarly, in a dedicated server network, client computers never act as servers. Client/server network includes one or more computers that are dedicated to acting as servers. The servers are optimized to provide quick access to shared network resources. Servers also provide centralized security to ensure that resources are not accessed by unauthorized users. Because the client/server approach centralizes control of data and other shared resources, one person or group is typically responsible for administering the network. Peer-to-peer networks. In peer-to-peer networks, every computer is capable of playing the role of client, server, or both at the same time. In this network, each computer on the network is referred to as peer. In a peer-to-peer network, a peer computer can act as both a server and a client at the same time. A peer computer on your desktop can share files and printers with other computers, and it can simultaneously access other shared resources on the network. A conceptual view of a peer-to-peer network is shown in Fig. 1.56. Peer-to-peer networks tend to be relatively small. Most of these networks fall to range between 2 and 10 computers. Large peer-to-peer networks become difficult to manage because so many network administrators control sharing and maintaining shared resources. Types of networks. The following are different types of networks based on the size and physical area they cover. Local area networks. A local area network, LAN, spans a limited physical area. It is confined to a single building or a group of nearby buildings. LANs are used for sharing applications, printers, group scheduling, email, project tracking, and other tasks. LANs is shown in Fig 1.57. Characteristics of LAN: spans a small physical area, uses high-speed wired/wireless connections between computers. It is a very reliable network. Communication errors are very rare. It consists of a limited number of computers. Wide area networks. A wide area network, WAN, spans a large physical area, connecting several sites of an organization across cities, countries, and continents. Because of the longer distances involved, WANs are sometimes referred to as long-haul networks. A WAN is often made up of two or more LANs connected together, as shown in Fig 1.58. Characteristics of WAN: spans a large physical area. It can be worldwide like Internet. Communication speed is slow compared to LAN. Connects computers through public networks, leased lines, or satellites. Connects multiple LANs. Sometimes communication errors occur due to its complexity. Metropolitan Area Network. Metropolitan Area Network, MAN, can span from several buildings or a large campus to entire cities. MAN is used by many organizations. It also connects a number of local area networks with high-speed communication lines. Characteristics of MAN: it is larger than a LAN and smaller than a WAN, covers an area of between 5 to 50 km diameter, provides high-speed communication, used by telephone companies, internet service providers, and cable TV companies. Virtual Private Network. Virtual Private Network, VPN, is a computer network that provides remote access to individuals and offices to their organization's networks. It provides cheap communication by using public telecommunication infrastructure, such as Internet, instead of expensive leased lines. It allows employees at home or on trip to connect their laptops into the computer as office through public telecommunication networks and do their work. Characteristics of VPN: it uses public networks such as Internet to connect computers, provides secure remote access, enables file sharing, video conferencing, and similar network services, provides cheap communication over long distance. Network topologies. The arrangement of network nodes, any devices which are part of network, and connections between them, is called the network's topology. A node represents any device on the network. Topology is simply a map of the layout of nodes and connections in the network. 4 network topologies are popular today, namely bus, star, ring, and mesh. Bus topology. Bus network topology connects each node to the network along a single piece of cable called a bus. Bus network topology is shown in Fig 1.61. Features of bus topology. Suitable for a small network. Easy to connect a computer or a peripheral device to the network. Requires less cable to implement. Terminator is installed at each end of the cable to prevent signals from reflecting back onto the bus and cause errors. Terminator is a device that is attached to ground. Limitations of bus topology. If the single cable is damaged or broken at any point, the entire network can go down. Difficult to identify the problem if the entire network goes down. Not suitable for large network. Star topology. In a star network topology, each network node is connected to a central device called a hub. Large networks can require many hubs, and hubs can be connected to each other to create a single large network. Star network topology is shown in Fig. 1.61. Features of star topology. It is suitable for both small and large networks. Easy to install and wire. Easy to detect and remove faults. Failure of cable does not stop the functioning of the entire network. Limitations of star topology. Failure of the hub causes the entire network to go down. Expensive topology to implement. Lengthy cable with a hub is required to install star topology. Ring topology. Ring topology is shaped just like a ring. It is made up of an unbroken circle of network nodes. Ring network topology is shown in Fig. 1.63. Features of ring topology. Each node is directly connected to the ring. Easy to install and wire. Data on the network flows in direction. Not costly to implement. Limitations of ring topology. If the ring is broken at any point, the entire network stops functioning, slower than other network topologies. Mesh topology. In mesh topology, each node is directly connected to all the nodes as shown in Fig. 1.64. Features of mesh topology. Most reliable network topology. Data can be routed around failed computers or busy ones. Can manage high traffic. Limitations of mesh topology. Most expensive topology to implement. Setup and maintenance is very difficult. Data communication standards. Data communication standards are a set of rules, protocols, and specifications that define how data is transmitted, received, and processed in computer networks and communication systems. These standards ensure that devices and systems from different manufacturers can communicate and work together flawlessly. Data communication standards play a crucial role in enabling interoperability, reliability, and efficiency in the exchange of data. The OSI Open Systems Interconnection is one such standard conceptual framework used in the field of computer networking to define and understand how different networking protocols and technologies interact and work together. Open Systems Interconnection, OSI model. The International Standards Organization, ISO, based in Geneva, developed standards for international and national data communications. In the early 1970s, ISO developed a standard model of a data communication system and called it the Open Systems Interconnection, OSI model. The OSI model consists of 7 layers. Each layer performs a specific task during data communication, as shown in Fig. 1.65. The 7 layers of OSI model are described below. Layer 7 Application Layer. Application layer provides services to end user. It interacts with the operating system or application software whenever the user wants to send files, read messages, or perform other network-related activities. Layer 6 Presentation Layer. Presentation layer takes the data provided by the application layer and converts it into a standard format that the other layers can understand. At the receiving end, it also formats the information so that it looks the way the user can understand. Layer 5 Session Layer. Session layer performs functions that enable 2 applications or 2 pieces of the same application to communicate across the network. It performs security, name recognition, logging, and other similar functions. It also establishes, maintains, and ends communication with the receiving computer. Layer 4 Transport Layer. Transport layer establishes connections between 2 computers on the network. It handles quality control by making sure that the data received is in the right format and the right order. Layer 3 Network Layer. Network layer decides which physical pathway the data should take to reach the destination. The communication device router works in network layer. Layer 2 Data Link Layer. Data link layer defines the format of data on the network. This layer converts the data into packets and checks them before putting them on the pathway. The communication device switch works in this layer. Layer 1, physical layer. Physical layer defines cables and signaling. It provides hardware, means such as cables and connectors for sending and receiving data. Cables, hubs, and repeaters work in this layer. Data communication protocols. Different communication protocols define how data is transmitted and received over a network. Examples include TCP/IP Transmission Control Protocol/Internet Protocol, used for Internet communication and provides reliable, connection-oriented data transfer. HTTP Hypertext Transfer Protocol, used for transferring web pages and related data on the World Wide Web. FTP File Transfer Protocol, used for transferring files between computers on a network. SMTP Simple Mail Transfer Protocol, used for sending email messages. The Internet. The Internet is a global network of interconnected computer networks that allows for the exchange of data, information, and communication among users and devices across the world. It is a vast and decentralized network that spans continents and connects billions of computers, servers, and other devices. Evolution of the Internet. The Internet has evolved from its origins in the 1960s as ARPANETU's Department of Defense project for research institutions and military installations to become a global network of interconnected computer networks. In the 1970s, the development of TCP/IP protocols established the foundation for the modern Internet, allowing different networks to communicate. The 1990s saw the emergence of the World Wide Web and web browsers, revolutionizing how people access and share information over the Internet. The 2000s brought broadband Internet and social media platforms, while the 2010s saw the rise of mobile Internet and the Internet of Things, IoT. In the 2020s, the Internet continues to evolve with cloud computing, artificial intelligence, and 5G technology impacting nearly every aspect of modern life. Working of the Internet. The Internet is the largest computer network ever built. It globally connects billions of devices and networks. It operates through a decentralized architecture using packet switching technology. Data is divided into packets, which are routed through a network of interconnected routers and switches. Protocols like TCP/IP ensure data is packaged, addressed, and transmitted correctly. The domain name system, DNS, translates human-readable domain names into IP addresses. Content is hosted on servers, and data is transmitted as packets to and from these servers. As data travels through the network, it is encapsulated in headers at each layer of the OSI model, such as the IP and TCP headers. When the data reaches its destination, these headers are removed through a process called decapsulation. Security measures like encryption protect data during transmission. The Internet's interoperable design allows diverse devices and networks to communicate, making it a global information and communication platform. Advantages of the Internet. The main advantages of the Internet include global connectivity, enables communication and access to information worldwide. Vast information, provides a vast information resources and knowledge. Communication, facilitates real-time communication and collaboration. E-commerce, allows online shopping and digital transactions. Education, supports online learning and research. Business, enhances productivity and global reach. Entertainment, offers streaming, gaming, and social media. Innovation, promotes technological advancements and research. Disadvantages of the Internet. The main disadvantages of the Internet include privacy concerns, threats to personal data and online privacy, cybersecurity risks, vulnerability to hacking and cyber attacks, information overload, overwhelming amount of data and misinformation, digital addiction, excessive screen time and online dependency,
digital divide, unequal access to the internet worldwide, online harassment, cyberbullying and harassment issues, health concerns, physical and mental health impacts. Common applications of the internet. Main applications of the internet include communication, email, messaging, and video calls, information retrieval, web browsing, search engines, and online databases, e-commerce, online shopping, banking, and digital payments, social media, networking, content sharing, and social interaction, entertainment, streaming, online gaming, and multimedia content, education, online courses, research, and e-learning platforms, research and innovation, access to research materials and innovation platforms, business and work, remote work, collaboration, and e-commerce.
Summary of computer systems. Computer systems are an integral part of modern life, transforming work, communication, learning, and entertainment. They consist of intricate hardware and software components that collaborate to process information and accomplish various tasks. Abacus, the abacus, invented by the Chinese 4,000 years ago, was a wooden frame with metal rods and beads used for simple arithmetic calculations. Napier's bone. John Napier developed Napier's bones, which used 9 strips marked with numerals for multiplication and division, introducing the decimal point system. PASCALINE, Blaise Pascal's 1642 invention, the PASCALINE, was first mechanical calculator consisting of gears and wheels. Stepped reckoner or LEIBNIZ wheel. Wilhelm Leibniz improved Pascal's device in 1673, creating the digital mechanical known as the stepped reckoner using grooved wheels. Difference engine. Charles Babbage's early 1820s invention, the difference engine, was a steam-powered calculating machine for basic computations. Analytical engine. Charles Babbage's analytical engine in 1830 was a mechanical computer that used punch cards, capable of solving complex mathematical problems and storing data. Tabulating machine. Hermann Hollerith's 1890 invention, the tabulating machine, based on punch cards, computed statistics and recorded data, leading to the creation of IBM in 1924. Differential Analyzer in 1930. Vannevar Bush introduced the first electrical computer, the Differential Analyzer, using vacuum tubes for calculations at a rate of 25 per minute. Mark I. Howard Eichen's Mark II, a digital computer invented in 1944, could add 8-digit numbers and print results using punched cards. It was 50 feet long and weighed 5 tons. First-generation computers. 1956 first-generation computers used vacuum tubes, were slow, expensive, and huge, relied on punched cards, and had limited memory. Second-generation computers. 1963 transistors replaced vacuum tubes in second-generation computers, increasing speed and reliability and reducing size and cost. Third-generation computers. 1971 third-generation computers used integrated circuits, ICs, instead of transistors, consuming less power and introducing keyboard and monitor interfaces. Fourth-generation computers. 1971 present, fourth-generation computers introduced microprocessors, becoming faster and smaller, and supporting advanced input/output devices, modern programming languages, and multimedia software. Fifth-generation computers. Fifth-generation computers aim to understand natural languages and possess thinking capabilities, relying on artificial intelligence, AI, and enabling user commands in any language. System. A system is a collection of interconnected components working together to achieve specific purposes found in various aspects of life. Natural systems. Natural systems exist in nature, are diverse and self-regulate. Examples of natural systems: ecosystems, weather systems, geological systems, hydrological systems, and the solar system. Artificial systems, human-made systems designed to solve problems. Examples of artificial systems: communication systems, information systems, transportation systems, energy systems, manufacturing systems, and healthcare systems. Input devices used to provide data to the computer, including keyboards, mice, microphones, scanners, barcode readers, digital cameras, and touch screens. System unit, the central part of a computer, including the motherboard, microprocessor, CPU, and registers. Memory types. Computer memory includes ROM, RAM, and cache memory, each with specific functions and retention properties. Output devices display text, graphics, and images, including monitors, printers, plotters, and speakers. Data transmission. Data moves between components through buses, following an instruction cycle that fetches, decodes, executes, and stores data. Von Neumann architecture explains how computer hardware and software work together, comprising a CPU, registers, AU, control unit, and buses. Memory units. Memory is measured in bytes, with various units like kilobytes, megabytes, gigabytes, terabytes, petabytes, adabytes, and exabytes. Memory built up. Memory can be chip, magnetic, or optical, and memory retention power categorizes it as volatile or non-volatile. Chip memory. Fast memory used in various devices like RAM, ROM cache, and SDES. Magnetic memory uses magnetized mediums like hard disks and magnetic tapes to store data. Optical memory stores data as bits and lands on optical disks like CDs, DVDs, and Blu-ray discs. Volatile memory requires power to retain data. Examples include RAM cache and registers. Non-volatile memory retains data even without power, including ROM flash memory and storage devices like hard disks and optical disks. Computer software. Computer software is a collection of programs, data, and instructions enabling computers to perform tasks. System software manages and controls hardware, acting as an intermediary between users and hardware. Includes operating systems, device drivers, utilities, compilers, assemblers, linkers, loaders, and firmware. Application software designed for specific user tasks such as productivity, business, entertainment, and education. Examples include word processors, spreadsheet software, games, and educational programs. Programming languages. Programming languages instruct computers to perform tasks. Low-level languages, machine and assembly, are hardware-oriented, while high-level languages, C++, Java, are user-friendly. High-level languages can be procedural, structured, or object-oriented. Data communication involves exchanging data between devices or systems via networks. Key components include sender, message, medium, protocol, and receiver. Modes of network communication. Modes include simplex, one-way, half-duplex, both ways, not simultaneously, and full duplex, both ways simultaneously. Transmission can be asynchronous, variable timing, or synchronous, fixed timing. Communication devices. Common devices include hubs, switches, routers, and gateways. Each serves specific roles in network communication. Network architecture includes LANs, local, WANS wide, MANS metropolitan, and VPANs, virtual private, defines the physical layout and connectivity of a network. Network topologies. Topologies dictate how nodes are connected. Options include bus, star, ring, and mesh. Each has unique features and limitations. Data communication standards. Standards like OSI establish rules for data transmission, ensuring compatibility and reliability in networks and systems. OSI model. The OSI model, developed by ISO, consists of 7 layers that perform specific tasks in data communication, including application, presentation, session, transport, network, data link, and physical layers. Data communication protocols various communication protocols such as TCP/IP/HTTP, FTP/EP and SMTP define how data is transmitted and received over network. Internet. The Internet is a global network of interconnected computer networks that has evolved from ARPANET to the modern era, facilitating communication, information exchange, and connectivity worldwide. Working of the Internet operates through a decentralized architecture using packet switching technology, protocols like TCP/IP/DNS for domain translation, and security measures to transmit and protect data. Advantages of the Internet. The Internet offers global connectivity, vast information resources, real-time communication, e-commerce, education, business opportunities, entertainment, and innovation. Disadvantages of the Internet. Concerns related to privacy, cybersecurity risks, information overload, digital addiction, the digital divide, online harassment, and health impacts are associated with the Internet. Common applications of the Internet. The Internet is used for communication, information retrieval, e-commerce, social media, entertainment, education, business, research, and innovation. For more interesting tutorials, please subscribe, like, share, and comment. Thanks.